This this lecture series is definitely something that we very much do together. It's the 20th in this. Sorry. Oh, it's the 20th in the Richard and Louise Guy lecture series. The series was actually originally originated in a 90th birthday gift from Louise to Richard Guy. Richard was long retired, but was still coming into the department 5 days a week, and that he continued to do that until he was 103 years old. Quite remarkably, he passed away in the middle of his 104th year, and that was in 2020. The lecture series is supported as well by the Department of Mathematics and Statistics and the Faculty of Science and by the Pacific Institute for the Mathematical Sciences. But like I said, the main funding for this comes from the endowment that Louise gave to Richard. And since the initiation of the series, we've had many wonderful talks from distinguished lecturers. And these lecturers have exemplified Richard's love of mathematics and his desire to share that passion with other people. And today will be no exception, I'm quite confident. So having said that, I'm going to just hand over now to Dr. Mark Bauer, who's the Associate Dean Teaching and Learning in the Faculty of Science and also a member of our department.
Thank you, everyone. So indeed, I am the Associate Dean, Teaching, Learning, and Student Engagement in the Faculty of Science. I also happen to be a mathematician, so it gives me great joy to be here today and to introduce our Guy Lecture speaker for the year, for this evening, Professor Joe Silverman, one of the world's leading mathematicians whose work has fundamentally shaped our understanding of number theory and its application to cryptography. Professor Silverman is currently a professor at Brown University. He's internationally recognized as a leading expert in arithmetic geometry, elliptic curves, and arithmetic dynamics. His work on elliptic curves has been absolutely foundational to the field. He's authored 2 graduate textbooks, The Arithmetic of Elliptic Curves and Advanced Topic in Elliptic Curves, Arithmetic of Elliptic Curves. Sorry, I don't know why I'm bumbling. I'm used to teaching calculus, so this is it's a different thing. And anyways, so these textbooks have sort of become the standard references in this field. These works were so influential, he's actually won the Steele Prize for Mathematical Exposition from the American Math Society. I can speak personally to the impact of Joe's textbooks. His books on elliptic curves fundamentally shaped my own understanding of this beautiful area of mathematics. The same textbooks have also guided my students, providing them with rigorous foundations and clear exposition that has become Joe's hallmark as a mathematical author. It is safe to say that the impact now extends to generations of mathematical students, mathematicians. What makes Joe's work, I think, particularly unique and remarkable is how he bridges the gap between abstract mathematical theory and practical applications. In 1996, he co-founded the N-True Crypto Systems with colleagues Jeffrey Hofstein and Jill Pfeiffer, developing revolutionary lattice-based cryptography systems that are now being implemented to protect against future quantum threats, and so perhaps we'll hear a little bit about that tonight. His publication history is very extensive and is beyond what one should enumerate in polite mathematical company. He's a Guggenheim Fellow. He's also received the MAA Award for Distinguished Teaching and served as an invited speaker for the 2022 International Congress of Mathematics. He's also a fellow of the American Mathematical Society, a recognition that speaks to his overall impact and commitment to the community, which is also evident through his extensive service on the AMS Council, Executive Committee, and Board of Trustees. Professor Silverman exemplifies the mathematician as both scholar and educator, advancing frontiers of knowledge while nurturing the next generation of mathematical minds. So this afternoon, he will be talking about how quantum computers could destroy the internet and what mathematicians are doing about it. Please join me in giving a warm welcome to Professor Joe Silverman.
Great. Well, thank you very much for that great introduction and for the invitation to speak today. And wow, thank you all of you for coming to listen to this talk. I hope you'll find it interesting. So let me just jump right in. One of the really important things that mathematics has done that's helped shape the modern world is the research that underlies the security of the internet and all the things that the internet has spawned, most of which really would not be possible without cryptography, which is what today's talk's mostly about. More specifically, what's known as public key cryptography. And the talk will include a handful of different types of things. I hope everyone will be interested in some of them, even if people aren't interested in all of them. There'll be some history, there'll be some mathematics, and there'll be some personal observations here and there. So let me start with cryptography back before public key cryptography, which is what cryptographers called the Dark Ages, which was basically before the 1970s. So here's the fundamental problem that people have faced throughout the ages. Someone who I'll call Bob wants to send someone I'll call Alice a secret message. So what do? First, they share some secret key. Then, after they've gone their separate ways, Bob encrypts his message using that secret key, and he sends the encrypted message to Alice. And Alice uses the secret key to decrypt the message and figure out what Bob really wanted to say. But you can immediately see the problem. They have to start by exchanging this secret key. So they either have to get together to do it, or they have to send it by a messenger and hope no one waylays the messenger. What can they do if they've never met? Well, as far as I can tell, up until the mid-1970s, no one had really thought about whether there was any other way to do this other than start out by exchanging a secret key. But in the modern world, say Alice was actually Amazon and Bob wants to send his credit card number. He's not going to go to an Amazon office and get a secret key first. So in the 1970s, mid-1970s, Diffie and Hellman proposed what they called a two-key cryptographic system, where there'd be a publicly available key, everyone would know it, and you could use that to encrypt messages. But there'd also be a privately held key, and only the person with the private key could decrypt the messages. I'll mention some of the secret services in the US and Britain actually had kind of come up with the same idea earlier, but they didn't publish it or even acknowledge they had thought of it till years later. Anyway, so here's how it works in pictures. It's supposed to work. Alice has her public key, and she publishes it. So Bob looks up her public key somewhere on the internet, and he takes the message that he wants to keep secret, and he runs his message and Alice's public key through the encryption machine. It's an algorithm. And out comes his encrypted message, and he sends that to Alice. Okay, Alice gets his message, the encrypted message. She feeds that and her private key that only she knows into the decryption machine, and out pops Bob's original message, and all is good. On the other hand, an adversary who only knows the public key can't decrypt the message because they don't know the private key. But something that's tricky to manage is you have to make sure that people who know the public key can't use it to figure out what the private key is. Otherwise, the whole thing falls apart. So what happened with public key cryptography? Well, Diffie and Hellman's really brilliant, groundbreaking paper, it attracted a lot of attention. It didn't actually include an example of one of these public key crypto systems. They just said, basically, this is what we'd like to do. We don't know how to do it. Here's something a little bit weaker that we do know how to do. But immediately, people started trying to figure out systems. And there were a handful of interesting constructions, most of which were very quickly broken. But two seemed pretty practical and weren't at least immediately broken. One of them is called the RSA crypto system. It was invented by Rivest, Shamir, and Edelman, and they named it after themselves. And the other was called a knapsack crypto system. So it was based on something called the knapsack problem, and that was invented by Merkle and Hellman. So Hellman's the same as in the Diffie-Hellman paper. Okay, so what happened? Well, the knapsack system was actually more efficient than RSA, so people initially were very enthusiastic about it. But then people used something called lattice reduction to break the proposed system. And there were variants proposed, and then clever people said, well, you can break those too, and it went back and forth for a few years, and finally people gave up and said, nope, those lattice-based knapsack systems were not going to be secure. And we'll come back to lattices later because they reappear in a major role. But in any case, RSA survived this and it prospered and it became the de facto standard. Although over the next couple of decades, other systems came to try to sort of challenge RSA's dominance. What was the government's reaction to Diffie-Hellman's paper and then the Rivest-Shamir-Edelman system? Well, they were kind of upset because they didn't want the general public having strong encryption systems, basically. So first, they tried to suppress distribution of the original RSA paper. Remember, this is pre-internet. You distribute a paper by typing it up, Xeroxing it, and putting it in mail. But Shamir wasn't a US citizen, so they didn't really have control. So Shamir basically just made a bunch of copies and shipped them off to colleagues all over the world. So that finished that. So then the NSA, the National Security Agency, instituted this voluntary pre-publication review process for crypto papers and said, well, when you have a crypto conference in the US, don't invite any non-US citizens. I mean, this was all nonsense. But their justification was this. There's actually a law in the books that said cryptographic materials are munitions. And exporting munitions without an export license actually qualifies as treason. So that wasn't so great. It was meant to secure things like the cipher machines that were used during World War II, and you really didn't want something like that shipped off to the enemy. Okay. But they finally realized that most of this was pretty futile. So what they ended up with was journal articles, conferences were fine, but they didn't want people exporting runnable code for these public key crypto systems. But there were optical scanners, so pretty much anything on a written page becomes readable by a computer. So this led to some very amusing objects, including this T-shirt for a while could not be exported because it was a munition, because you could optically scan the RSA algorithm off of it. Same thing for the soda can. Someone actually tattooed this onto their body, making themselves a munition. Okay, so that's a little bit of the history. Now I'm going to shift over and do some of the math. Public key crypto systems and these other things called digital signatures, which are similar but a little different and are very important, they're built from what are called trapdoor functions. And the idea is if you have a trapdoor function, you can find the treasure if you know the trapdoor. So this is my attempt to draw an illustration of that using ChatGPT yesterday. I don't know how successful that was. Okay. More formally, what's a trapdoor function? It's a function where it's really easy to compute. If I give you the value of x, it's really easy to compute the value of the function f of x, or at least easy for a computer to do it. But it's really hard to go the other direction. If I give you the value of f of x, call it y, it's really hard to find the x value that it came from, unless you know this extra piece of secret information, the trapdoor. then it becomes easy to find the x if I give you the f of x. And if you can build one of these functions, you can build a secure public key crypto system. At the moment, we don't actually have any such functions that are provably trapdoor, but there are a lot of functions we think are trapdoor. So I want to give you a moment to get your heads around that. All of your internet security is based on the belief that these functions actually have this property. And I'm going to describe some of the functions without describing how to turn them into public key crypto systems, which would sort of take us a little too far astray. Unless people want a 3-hour lecture? No? Okay. So let me describe a few of these functions. The first one is integer factorization, just factoring whole numbers, which probably people have been doing ever since they started using numbers, right? I mean, 6 is 2 times 3. That's different from 5, which isn't, a product of 2 things. So given 2 large prime numbers p and q, I'm going to look at the function that takes a number, raises it to the nth power, and then this mod pq means divide it by the number pq. You have a number, integer, x to the n, divide it by pq, take the remainder. In other words, elementary school division with remainder. And it's very easy to compute this. If I give you x and I give you n and I give you p times q, it's easy to raise to powers. It's easy to divide and get the remainder. Okay? But if I give you that remainder, it's very hard to go back and figure out what the x is if you only know the product p times q. But if you know the individual numbers p and q, then you can find the x. Okay? So that's the trapdoor. The trapdoor is knowing the individual p and q as opposed to just knowing their product. And this is what Rivest, Shamir, and Edelman based their RSA crypto system on. And this problem is what protects most of your internet commerce these days. A similar sort of problem with sort of a slight reversal, it's called the discrete log problem. And I know everyone loves logarithms, but even if you don't, the problem, and it's a similar thing here. Given a number m, I raise a number g to the nth power, so I just multiply g m times, and I divide by p and take the remainder. Okay? So again, it's very easy to do this kind of exponentiation and remainder stuff. What's hard is if I give you the remainder, it's very hard to reverse it and figure out what the m was, what the exponent was. Figuring out exponents is a logarithm problem. That's where the name comes from, but it doesn't really matter. The thing to notice here is, given the remainder of g to the m, it's hard to figure out what m is. So in this case, Alice's secret key is going to be the m, and her public key is going to be the g to the m. And it's hard to reverse. And this is called the El-Gamal public key. It's used to build the El-Gamal public key crypto system. Okay, since Mark made all these nice comments about elliptic curves, I'm going to mention elliptic curves. I'm not really going to say what they are. But elliptic curves are used to build a crypto system sort of like the El-Gamal system. But instead of, let me go back here. Instead of raising things to powers, an elliptic curve has a way of, it's a curve and it has a way of adding points. So instead of raising a number to a power, you add a point to itself a bunch of times. Okay? It's called the elliptic curve discrete log problem. Whatever an elliptic curve is. Here's a couple pictures of elliptic curves, and I said you can add points. So you add these points by drawing a line, and you intersect, you draw a line, you intersect, whatever. There's a picture and there's a formula. Formula is not so complicated. So it's relatively easy to add points. And this is used to build the elliptic curve version of the El-Gamal public key crypto system. Why? Why would someone do this? Well, the idea of using elliptic curves was proposed independently in the mid-1980s by Neil Koblitz, who was a professor at the University of Seattle, and Victor Miller, who was a researcher at IBM. And it's quite widely deployed. Interestingly, I mean, the first thing Ravesh Shamir and Edelman did was they patented their idea. Although they applied for a US patent, not other patents worldwide, so it was only patented in the US. Neither Neil nor Victor actually applied for a patent. Neil doesn't really believe in them. Victor was working for IBM. I still have no idea why IBM didn't patent it. I assume they sort of patented every research paper. Anyway, it wasn't patented. But why would anyone do this? I mean, I said addition of points isn't so complicated. It's a lot more complicated than just multiplying numbers. Why would one bother? Well, after a number of years of looking at it, it seems that the elliptic curve problem is harder than the original problem, significantly harder. So that means that if you use it for a crypto system, you get the same security with smaller key sizes, smaller message sizes, smaller signatures. And out in the real world, as academics like me quickly found out, it's all about efficiency. But with cryptography, there's a catch. It's efficiency, but you can't break the security, because if it's not secure, it's useless. So people use elliptic curve crypto where you need efficiency, and especially where you need small size keys, small size digital signatures. So a couple examples, well, okay. You may not, but I have in my pocket, in fact, an elliptic curve digital signature, because it's in the barcode on most airline, you know that square barcode thing on your airline to check in? Yeah, those normally have an elliptic curve digital signature on them for security reasons. Maybe even more important, virtually all blockchains, including Bitcoin, use elliptic curve digital signatures. Keep that in mind. The security of the trillions now? Certainly many billions of dollars in Bitcoin and other cryptocurrencies. One of the things that's keeping it secure is elliptic curve digital signatures. Okay, so what I want to talk about now and actually give you a few more details of is another kind of trapdoor function based on what's called the closest vector problem. This slide is for the mathematicians, the math students in the audience. The next slide will have pictures illustrating, so it should be fine. But formally, a lattice, it's kind of like a vector space. So you take a bunch of vectors, v1 through vn, that are just n tuples of numbers, and you look at all their linear combinations. But it's a little different from the linear algebra that gets taught in freshman or sophomore level, because the coefficients are only allowed to be integers. Okay? That's what a lattice is. And the closest vector problem is if you're given a lattice, which is a bunch of points sitting out in space, and you're given some point, some vector, you have to find the lattice point that's closest to the target point. Okay? And this v1 through vn is called a basis, but lattices have lots of different bases, and some of them are good and some of them are not so good. And I'll talk about that also. So the closest vector problem trapdoor is that it's easy to solve this problem if you have a good basis, and it's hard to solve if you have a bad basis. So I assume that's plenty of verbiage. Let's do some pictures, which should make things a little clearer. Here's a picture of a two-dimensional lattice. The lattice is the black dots. The vector v1 and v2 are the generators. This point is v1 plus v2. This point is 2 times v1, and so on. You just get all the dots. There'll be dots down here too, but I didn't draw them. Okay? So there's what you're given. You're given the black dot. You're given v1 and v2, so you can generate all the black dots. And there's your target vector. I just kind of picked a random vector. And your mission, should you choose to accept it, is find the black dot, the lattice dot that's closest to T. Okay? Everyone solved that? Good. Yeah, it's easy, right? You just eyeballed it. I mean, clearly, this dot that I marked as V, that's the lattice dot that's closest, because these are further away, and then the others are even further. So that was really easy. And the problem's still easy in 3 space. In 4 space, a little harder to visualize. Even in 50-dimensional space, it's actually not that hard to solve algebraically, but it becomes very difficult in high dimensions, like dimension 1,000 to 2,000. Okay? So all you have to do is imagine a regular pattern of dots like that, but instead of in 2 dimensions, the plane, just in 1,000 dimensions, okay? Yeah. Hard to visualize, easy to work with on a computer. All right, I said the problem's easy to solve with a good basis, hard to solve with a bad basis. What distinguishes them? Well, this picture has 2 bases. It has basis V1, V2, that's a good basis, and a basis W1, W2 that you can also use to generate all the dots. That's a bad basis. Good bases have vectors that are pretty perpendicular to one another. You can't get them completely perpendicular, but reasonably perpendicular. A bad basis consists of vectors that aren't perpendicular at all, right? They just make a tiny angle between them. Okay? And if you know a good basis, you can solve this closest vector problem. You can find the lattice point closest to the target. If you have a bad basis, it's, well, basically no one knows how to do it without using the bad basis to somehow create a good basis. And that's the hard problem. Okay, how do we build a crypto system from these lattices? Well, in the mid-1990s, Atay and Dwork, in a very important theoretical paper, which actually didn't have anything that practical in it, and Goldreich, and Halevi, sort of building on that, gave something that wasn't provable but was more practical, came up with a system where the private key was a good basis. Okay? So in the picture, the private key is knowing the V1 and the V2. The public key is the bad basis, knowing the W1 and the W2. And they gave a way to create a crypto system, a public key crypto system out of this. Unfortunately, the systems were definitely insecure in dimension 100 or 200, but they seemed fine in dimension 1,000 or 2,000. And they were very fast, much faster than RSA, much faster, orders of magnitude, faster than elliptic curve systems. What's the problem? Well, the problem is the public key is this bad basis. So a basis consists of n vectors. Each vector consists of n numbers. That's n squared numbers, each of which, so if n is 1,000, that's 1,000,000 numbers. And here I mean, 1,000,000 numbers, say 8-bit numbers, that's a megabyte. That's fairly big. I mean, I know these days that's not that much storage on your phone, but a megabyte is pretty big if someone like Amazon wants to store, hundreds of thousands of these. And by comparison, the RSA keys are 256 bytes. So compare that with 1,000,000 bytes. And here you can see actually with a number why the elliptic curve stuff gets used. The elliptic curve keys are only 32 bytes. They're much smaller than the RSA keys. These are the sizes that are sort of used currently. Okay, so at the same time, working independently with no knowledge whatsoever of this other work, Jeff Hofstein, who's an analytic number theorist, works mostly in automorphic forms, went to a talk that talked about RSA and decided that there must be a more efficient way to do public key crypto, so he started thinking about it. And after a bunch of constructions, he came up with this system that uses ring theory. So again, for the mathematicians in the audience, he used a quotient ring. And the private key were a couple of polynomials with small coefficients, like 0, 1, -1. And the public key was another polynomial whose coefficients were between 0 and q. Okay, so the details don't matter so much. What matters is that the public key was just this single H. It wasn't a list of n different things. And Jeff, talked to some people about it. I guess he was at Berkeley on a sabbatical at that point, and he was talking to Bjorn Poonen, who pointed out that this ring system Jeff had come up with could be reformulated as the closest vector lattice problem. So it was related to these lattice problems. And the great thing about Jeff's system was the public key is this single polynomial, so it's which has n coefficients, so you only have n numbers instead of n squared numbers. And that in turn meant that Jeff's system would be comparable to RSA. So what Jeff did was he recruited two of his colleagues. So I'm going to put my phone on because I want to keep the time visible here. Good. So he recruited Jill Pfeiffer and me to help with the development, because going from a theoretical system to something you can actually implement is a significant task. Because again, because of that efficiency versus security, in this case, you want to take n as small as possible while making sure people can't break it. But eventually it became what's now known as the n-true public key crypto system. So what happened when n-true went out there in the real world? Well, Jeff, I really want to stress the idea was Jeff's, and he deserves a lot more credit for lattice-based crypto than he gets. And Jill and I helped him, but it was really his brilliant idea. Anyway, so he'd invented this new public key crypto system. It was an order of magnitude at least faster than RSA and elliptic curve stuff. And it had key and message sizes comparable to RSA. So, of course, right? N-true was instantly adopted. Everyone started using it. Jeff became rich and famous, and happy ending to story. Yeah, no, not in the slightest. So what happened on the math side, we worked out the details of how n-true would work. This took a year or so. We submitted a patent application. In fact, what I did was I got a book called How to Patent Your Idea, or something like that, read it, and we talked to a patent attorney. That was actually pretty interesting. We wrote and submitted a paper to one of the top crypto conferences, and we gave some talks at seminars. I actually gave a talk at IBM. So that was all good. But, ouch, paper was rejected. I see at least one cryptographer in the audience nodding. That's what happens. Okay, but two brilliant cryptographers, well, Shamir, who's the S in RSA, was already very famous at that point, and Don Coppersmith, who was maybe less well known among the general math crypto community, but who was in fact one of the, if not the, best cryptanalyst in the world who wasn't working for an agency like NSA. He was at IBM at the time. They found the idea pretty interesting, and they looked at it, and they said, hey, here's an idea to break it. So they wrote a paper with an attack on our crypto system, but purely theoretical. Basically said, since this is true, it seems that maybe this is true, and then it's broken. Yeah, their paper was accepted. So now we've got an attack on our crypto system we hadn't even managed to publish. And it was purely theoretical. So we spent 6 months checking, and the Coppersmith-Shamir idea was very interesting, but it did not work. Basically, if you implemented it, it would let you break the system, I don't know. If it took time t without their idea, it took 99% of t with their idea. So it really didn't make any difference. So we finally submitted our paper to a conference called it's called ANTS, Algorithmic Number Theory Symposium, which had been going on for a few years and is still going, actually. I just went to the one at MIT this past year. It's a great conference. And hooray, it was accepted. But no, this wasn't a cryptography conference. Okay. So the outcome of all of this was, first, people had been skeptical about lattices in cryptography ever since that knapsack system was broken. And then there was the Coppersmith-Shamir paper. So for years, when we gave talks about entropy, people said, oh yeah, but Coppersmith and Shamir broke that. Because their paper had been out there for more than a year before our paper appeared. Anyway, that was annoying. But not that we're bitter. Okay, that's sort of in academia. What about out in the real world? So I wrote here, what happens when 4 academics with no business experience try to monetize a mathematical invention? And I mentioned Jeff and Jill and me. The fourth person was a former student of Jeff's named Dan Lehman, who kind of joined us for this effort. Well, things went pretty well. We got some seed money from Sony, which we could use to hire a CEO and a chief engineer. And the chief engineer had worked at RSA, so he knew the commercial crypto industry. They put together a real business plan that we obviously were not capable of doing, and went around to venture capitalists and managed to raise over $10 million in venture capital money, which was great. So we built a company. We rented and furnished an office, which we were told in a company like this, the essential is having a pool table, so we did. We hired engineers, marketers, support staff, all of whom kind of speak different languages, so it was an interesting educational experience, learning how to talk to everyone. We started developing products, but we didn't have any customers yet. So what do you do when you're developing products and don't have customers, and it's during the dot-com era? You don't continue developing products and try to get customers. No, you go out and raise more money. So they went out, they put together a secondary business plan, and they raised $30 million more. So we now have more than $40 million in the bank. But the VCs want us to spend it faster. What they'd really like is products and customers bringing in revenue, even if the revenue is not covering the expenses. Because then it looks like it might build, and then you can either go public or you can sell the firm to another company or something. Because VCs are basically in for 3 to 5 years, then they'd like to get out and make money on their investment. So that's fine. Okay, so we started trying to figure out how to spend more money, which is harder than you think. But remember I mentioned this was during the dot-com boom, and that didn't last. Bang. The dot-com bubble burst, and the VCs came in, and they said, we're going to take back all our money, which contractually they were actually entitled to do. But we managed to convince them to leave at least a few dollars, so they left us, can't remember, maybe something over $1 million, which meant we had to fire a lot of people, but not everyone. And I'm going to summarize in the next bullet point roughly 20 years worth of stuff, maybe even more. So we consolidated, which we had to do, obviously. And we developed some profitable products. When I say we, I mean the software engineers mainly, who were really, really good. But non-proprietary cryptography products that they put together packages that were better than anything else on the market. So that was a really saleable item. We merged with another company who were mainly interested in these non-proprietary packages. They weren't so interested in things like Entru. So eventually we spun the intellectual property off into a new company and sold it to a larger company, and we all made some money, but no one got super rich. If I had my own yacht, I probably wouldn't be here. Well, actually, I probably would. I love doing things like this. Anyway, so I guess it's probably time for me to actually get to the topic that I put into the title of the talk, which I'll mention. I was just telling people, when I showed it to my son who's a software engineer, he said, great clickbait title, Dad. So quantum computers. what is a quantum computer? If you really want to know, you're not going to find out tonight. But I can give you a little idea. So an ordinary computer, which is what you have in your cell phone and your laptop, has a bunch of registers which are bits. And each bit is either 0 or 1. And they flip back and forth, and that's how it does computations. Quantum computers have quantum bits. They're called qubits. And why do we care about any of this? Well, because in 1994, Peter Shor wrote this paper called Polynomial Time Algorithms for Prime Factorization and Discrete Logarithms on a Quantum Computer. You wouldn't think a paper like that would threaten the entire internet infrastructure, but it does. What did Shor do? He described what are known as quantum algorithms that would run on a quantum computer, which did not exist, that could solve integer factorization. Remember, that's the problem that underlies RSA. And discrete log problems, that's the problem that underlies those elliptic curve systems in, well, what's more or less quadratic time, if you want to be technical, but where it says more or less quadratic time, read really quickly. Those systems are dead if you could do this. So anyone who could build a full-scale quantum computer will be able to break all of the classical and all of the widely implemented public key cryptography that's currently used. Okay? Because these problems would no longer be hard. So maybe one slide sort of illustrating a little bit about a quantum computer. So this is what 8 bits on a classical computer looks like, zeros and ones. If I were more adept with PDF slides, I'd kind of have zeros changing to ones and ones changing to zeros. So visualize that as it's doing computations. But each of the little squares has a 0 or a 1. This is what 8 qubits looks like. Those Greek letters there represent, well, in the popular literature, they represent a number that can be any number between 0 and 1. You know, the first one could be 0.35, and the second one could be 1 over pi, and the third, so, okay? That's not a bad way to think about it, but a little more accurately, for the mathematicians in the audience, the qubit's actually a complex number, really, that represents a superposition of 0 and 1s, where 0 has a certain probability and 1 has a certain probability. And the probability is measured by the absolute value of that complex number. And then the probability distributions change as you're doing these quantum computations. It sounds complicated, it is a bit complicated, but the net result that Shor pointed out was that if you had a quantum computer that had n bits, you could simultaneously do 2 to the n computations. You could do exponentially many computations. And that really speeds things up. Gives you an exponential speed up for some problems. For integer factorization, for the elliptic curve problem. So here's where we currently stand. If you could build a quantum computer in your basement, a big one, you could do integer factorization exponentially faster. RSA is broken. You could do discrete logs exponentially faster. The elliptic curve systems are broken. Closest vector problem actually just gets a little bit faster. So the lattice-based systems like ntrue turned out not to be broken. So although people really weren't interested in ntrue when it was a little bit, well, when it was much faster than RSA, but that was its only advantage. And the reason is sitting in your cell phones. Processors got so much faster, it didn't matter. But now, if RSA is going to be broken, they need a replacement. And people started looking at lattice systems a little more closely because Shor did not come up with a quantum algorithm to solve lattice problems. In fact, he proposed that as a good place to look for, to try to solve. And what did I say? That was 96, right, or something like that. So 30 years later, people have been trying to solve lattice problems using quantum computers and have not come up with an algorithm. That is all that our idea of security rests on, that a lot of clever people, smart people have been working on it and they haven't solved it. But of course, that's what RSA was based on also. Okay, so why should you worry about this? Well, you would need a quantum computer with somewhere between 10,000 and 100,000 qubits to break RSA and to break the elliptic curve systems, okay? So how big is that? Well, in terms of classical computers, I mean, how many bits do the processors on your cell phone have? Yeah, a lot more than 100,000. So rather than put a whole slide with the progress, I mean, the first quantum computers people built were sort of molecular based. And I still remember there was an article that someone had managed to build a quantum computer with, I think it was maybe 8 quantum bits. And they used it to factor 15. That was 3 times 5. But people have been working since then. It's a mix of very, very smart engineers and very, very smart physicists working together on this. And there's a lot of money being poured into this. So the largest quantum computer I could find out about online when I did a search the other day was an announcement by IBM just a couple of years ago that they had an 1,100-bit quantum computer, 1,100 qubits. Okay. Well, you know, back in the days when people were building 8 and 10 and 12-bit quantum computers, 100,000 qubits seemed out of reach. But you know, there's not that much. I mean, that's over 1,000, and we're talking just one more order of magnitude, or maybe 2. All right, so this is the analogy I like. The first mechanical flight using, of a heavier-than aircraft was in 1903, and it went all of 852 feet. It took less than 20 years for you to have airplanes flying over World War I battlefields. And it took less, well, okay, not less than 20 years, 25 years maybe, to have jets that were going 500 miles an hour. Okay, so if you think of the 8 quantum bits as the Wright brothers airplane, and this IBM thing is the World War I planes, when are you going to have the World War II planes? Well, maybe not for a few years, maybe 10 years, maybe 20 years. But here's why you want to worry about it now. And there are probably other reasons, but one, a breakthrough can occur at any time, right? You never quite know when someone's going to have a brilliant idea that's suddenly going to make things much faster. That happened with RSA, with integer factorization. There was this big breakthrough called the number field sieve, which suddenly meant RSA keys had to be made significantly longer, not unusably longer, but significantly longer. How low do you want your secrets and contracts and bitcoins to be secure? Okay, if you sign a contract today for a piece of property, you don't want someone to be able to forge or show that contract's invalid, right, 30 years down the line. And even if you're just protecting, say, Bob sending his credit card number to Amazon, and it's going to be 10 or 15 years before someone builds a big enough quantum computer to break all the internet security, it takes a long time to retrofit all the algorithms on the internet. And in fact, there are a lot of programs still out there that are using crypto systems that have been broken. Hopefully not for things that are too crucial. Okay, so there's 3 good reasons to worry now. So what's been happening in the real world? Well, about, 10 years ago, roughly, the US National Institute of Standards and Technology, this goes by the acronym NIST, released a report on post-quantum cryptography. which they didn't just prepare internally. They had conferences, they consulted people in academia and in the business world and in government to try to figure out what people could look forward to in the not so distant future. And their report ended up with an estimate that it was likely that a quantum computer that could break a 2000-bit RSA, which was the standard at the time, in a matter of hours, could be built by 2030, that's coming up, for a budget of about $1 billion. Okay, show of hands, who has $1 billion that they could use to, yeah. But governments have $1 billion. Businesses have $1 billion. Probably criminal enterprises, many of them, or at least some of them have access to $1 billion. And they'd be happy to spend $1 billion to build a quantum computer that could, say, siphon off all the value in Bitcoin. That would be a good investment. Not so good for the owners of the Bitcoin. So what NIST did, rather than try to rig up on their own a new way to secure internet communications, they opened a competition, which is they had been doing for a while. They'd done a bunch of competitions of various kinds of cryptography to try to create new crypto systems, because what happens is if you have a small group of people who come up with a crypto system and they analyze all the possible ways to break it and they think it's secure, they're probably wrong. You need a big community of people looking at things over a matter of years and bouncing ideas off of each other. So NIST has had a number of these competitions, and they instituted a competition for post-quantum cryptography. And what they were looking for was digital signature systems and public key encryption systems that were capable, well, their interest, protecting government information, including after someone builds a large-scale working quantum computer. And I mean, they're also interested in protecting commerce. So, okay. So here's a rough, I took a lot out, so I just fit some of it on one slide, how the NIST competition proceeded. It started in 2016. There were 56 crypto systems and 23 digital signature schemes that were submitted. There were many research papers and conferences and stuff. And a bunch of the systems were broken. And they picked a certain number of the remaining ones to be round one finalists. More conferences and papers and things. And so in round two, get up to 2020, so 4 or 5 years later, they got down to round three. There were 4 crypto systems and 3 signature schemes, most of which were either lattice-based or elliptic curve-based, but not the elliptic curve discrete log problem that I had mentioned earlier. That one would be broken by a quantum computer. People had come up with a different way to use elliptic curves. Very clever, very interesting, that as far as people knew, there wasn't a quantum algorithm for. So those were the main 2 competitors. There was one other, which I won't mention, that also was there. And after the round 3 finalists were announced, then people really dug in to those 3, both from security viewpoints, trying to get the most efficiency while remaining secure, of course. So there was a lot of tinkering on the edges. In fact, 2 of the crypto systems, I think that was the point at which 2 of the cryptos, no, actually maybe it was a step before that. So at various points, some of the proposals were similar and they kind of got merged with the best aspects of both. So finally, in 2022, NIST made the final selections. And at that point, they said, here are systems that you should start implementing to guard against quantum computers in the future. They didn't say, start using them now. They said, start building them into everything so that when you need to, you can flip a switch and start using them. Okay? And there was one crypto system, it's lattice-based, and there were 3 signature schemes, 2 of which were lattice-based and 1 of which is what's called code-based. They also didn't throw away all the other finalists. They targeted a few alternatives, including an elliptic curve crypto system, saying, these look good, but we still don't quite feel they're trustworthy enough. We want more work done on them. And in some ways, it's good that they did, because shortly after they announced this, one of the elliptic curve systems that they had proposed, oh, actually, okay, I'm going to do these out of order, was broken. And it was really badly broken in the sense that someone figured out how to break it on their laptop. They had an algorithm to break it on their laptop. They didn't need a supercomputer or anything. And the nice thing, it used some very serious mathematics from a paper of Ernst Conny in algebraic geometry from the 1990s. So you never know what's going to be helpful. But I did also want to mention that I kind of like to think that the lattice-based systems, although they're not exactly n-true, they're progeny of n-true. And one of them, one of the signature schemes, called Falcon, actually is a direct n-true descendant of an n-true signature scheme. The others use slightly different lattices, but the whole idea is to use lattices efficiently, you need a ring-based structure. And that was Jeff's innovation, to put a ring-based structure in so the keys would get to a usable size. And everything there uses rings. So that's about how things stand now. People and businesses and government, I assume, are starting to implement these things since it was announced a few years ago. If they're not, they certainly should be. So let me just leave you with a few words that quantum computers are definitely, I would say, are definitely coming. Next year, probably not. By 2030, as in the NIST report, possibly. By 2040, pretty good chance. So you should start preparing now, preferably with lattice-based cryptography. So I want to thank you all very much for your attention, for coming. There's a huge audience. I really appreciate it. I want to thank the organizers of the Louise and Richard K. Guy lecture series for inviting me to speak. And thank you very much.
Thank you very much, Joe. We have some time for questions. We will have a roving microphone. Is this the roving microphone? Okay. So if you have a question, please put up your hand and the microphone will come to you. And if you're online, please email your questions to
scievents@ucalgary.ca.
It's on the screen. Fantastic. So.
Thank you. So I was wondering, in terms of that key, this might be beyond the scope of this presentation, but in terms of that like surviving crypto system that the NIST selected, could you explain sort of roughly how that works, or is it just sort of? I take it, of course, it is currently still believed to be sort of impervious to quantum computers.
The public key crypto system, I think it's based on the learning with errors problem, but ring-based learning with errors. So it's similar to n-true in that you have sort of a linear equation in some ring, and you're reducing it mod p, and you're introducing a small error term. Yeah, so that's the underlying problem there. Yeah.
Okay, thank you.
Sure.
Hello. So the moral of this story is quantum computers are coming and you'd better prepare. But I'm not in the business of building crypto systems or secure banking websites or anything like that. So is there anything that I, as a person, can do to prepare for the coming quantum revolution?
I would say no.
Figures.
Other than if at some point, someone like IBM or less likely the US government or China or something announces that they have 100,000 qubit computers, I might start looking to see which companies say, we're using quantum secure cryptography for our transactions. Similarly to the early days of the internet, there was web browsers, some of them were using stuff that was secure and some of them were using stuff that was kind of sketchy. And people who looked into it would use the more secure ones. Yeah.
Thank you.
You're welcome.
This is all incredibly scary. You've talked about it in the context of Bitcoin, but everything financial is now sitting on a computer. I talk to people all the time who are, scared to do their banking on the computer. They don't want to access it. They don't realize that their money is already on the computer. So all our money, all our investments, all our property records, everything is sitting on a computer someplace. And the message I'm taking out of this, without some additional security, all of that is up for grabs by the dirtiest person who can figure it out. Am I gone too far?
No, in some sense, yes. If someone has a 100,000 qubit computer in their basement now, yeah, pretty much. However, assuming that these banks and financial institutions are smart enough, and I'd like to think they are, they're having people program in these new NIST systems, and they'll start using them over the next few years. And at that point, you're still secure, because it's the same financial records, but to get into them, you'd have to break one of the NIST systems, which quantum computers can't. Something like Bitcoin's a little trickier, because it's out there already, and it's not clear to me you can retrofit quantum secure digital signatures into the blockchain signatures that are currently all elliptic curve based. So I'm sure people are thinking about it, people who know a lot more than me. Hopefully they can. But even if they do, the signatures are going to get about 10 times longer, I think. And that may slow blockchain operations down. So it's things that are out there that are hard to change that I'm much more worried about than companies that are using classical security now and they just need to reprogram in new algorithms. Yeah, hopefully they'll do that quickly. Yeah, thank you, great question.
I'm going to steal a question from online. So the question is, have any AIs come up with crypto algorithms or ways to break existing crypto algorithms yet? If no, how plausible is that to happen in the near future?
Also, great question. And I think it's probably, everyone who works in lattice-based crypto, once these AI systems came in, their first thought was, well, there are algorithms to try to solve the closest vector problem, okay, to break these. And the way you measure the security is you measure how fast the best known algorithms can solve the given problem. And you want that to be, tens of thousands of years. And those algorithms work by, remember, you start with a bad basis and you want a good basis? Well, you don't go directly. You take the bad basis, you make it a little bit better, you make it a little bit better, you make it a little bit better. And the path to making it better it's not clear quite how to do that. And the question was whether AI would be able to see patterns to find a better path to go from a bad basis to a good basis. And I know there are a bunch of groups working on that, including a significantly sized research group at one of the larger companies. And every talk I've heard so far has been fascinating and fascinating ideas, and the result has been no. These AI systems do not seem to be able to learn how to solve lattice problems the way they learned how to play Go, for example. Yeah. But why they can't is no one knows.
So what is holding these companies back from making these computers greater than around 1,000 qubits? Why can't they just, say, stack 10 or 100 of them side by side to then get that computing ability?
Okay, now you're getting outside my expertise, because I really don't know quantum stuff much. But my understanding is that there's a matter of the coherence between the qubits, that they need to interact in various ways. But yeah, if you want a full answer, you'll need to ask someone who actually knows about quantum, how people construct quantum computers. Yeah.
Thank you. A little technical question, but while explaining the closest vector problem, you said that the basis we choose should not be perpendicular, they should be near perpendicular. But like in my mind, if we just choose an orthogonal basis, wouldn't that make finding the closest lattice point a lot easier?
Yes. If you started with an orthogonal, orthogonal means all the vectors are perpendicular to each other, basis, it makes the closest vector problem trivial. But it also means that essentially there are no bad bases. So yeah, so you want a lattice that's, the generators are, you want a reasonably random lattice. And in a reasonably random lattice, there will be a basis that's fairly orthogonal, but it won't be fully orthogonal. And then when you use that to create a bad basis, it's hard to go back and forth. If you have a fully orthogonal basis to start with, it turns out the problem's too easy. But that's a good question. You're right. It would be much more efficient if we could do that.
Yeah. Thanks for the talk, Dr. Silverman. I had a question about the difference between these hard problems. Is it like the computational complexity of this lattice problem fundamentally different than, let's say, integer factorization problem or elliptic curve stuff, in such a way that even an exponential speed up won't make much difference? Or is it because of some other reason that Shor's algorithm is not applicable? Or
yeah. Well, an exponential speed up in solving closest vectors would kill the lattice-based systems also. Pretty much all of the quantum algorithms, like for integer factorization, for discrete logs and things, they rely on an underlying cyclic structure. And what they're capable of doing is finding certain subgroups of certain abelian groups, basically. And the entry lattices, and even sort of more general ring-based lattices, the underlying groups are non-abelian. And at this point, no one's come up with quantum algorithms that can solve these non-abelian things. Why? I don't have a good reason for it. I don't really work in quantum algorithms. But that's sort of an underlying difference between them. The problems quantum breaks nowadays have an underlying cyclic structure that the lattice problems do not.
right. Thank you.
Thank you for your talk. You said that there's just the one lattice-based system that was chosen in the NIST competition. If tomorrow someone finds a fast algorithm to break lattice stuff, what are other options? It seems like I feel like we would want a little more variety for the entirety of the internet's infrastructure.
That was one of the reasons for NIST competition. They wanted to find a bunch of different ones that they thought would be trustworthy. Yeah, if someone breaks that particular, I mean, you can go from closest vector problem and turn it into a crypto system in various ways. If someone breaks that specific implementation, it probably means there was a small flaw in it and it could probably be fixed. If someone breaks closest vector problem, all but one of the systems NIST chose as for people to implement would be broken. The one that isn't broken is called a code-based system. The problem with the code-based systems is, although encryption decryption is very fast, the keys are very, very large. They're more like megabyte-sized keys. So in worst case scenario, I guess we could go to use those. You can also base a public key crypto system on code-based system. But again, the keys would jump orders of magnitude in size. Would slow down the internet a bit, would make blockchains really hard to implement. I think, and those original 56, it was 56 crypto systems and I can't remember, 20, 30 signature schemes that were submitted. A lot of them were based on a lot of different kinds of problems, but they were either broken or there were reasons that they felt insecure. It would be nice if there were more problems. Though keep in mind, for the first 10 years of this, the only problem that was being used was RSA integer factorization. And then people started using the discrete log problems, and that was it for another 20 years. Yeah. Too many eggs, too few baskets.
All right, so maybe one last question just from online. I never quite understood why we can't use an NP complete problem as the basis for cryptography. They are pretty secure. I guess the issue is encryption efficiency, but is there a no-go result?
It's efficiency. NP complete problems, tend to lead to inefficient cryptos. If you want something that's provably equivalent to an NP problem, on the other hand, I'm trying to remember. Again, not my area of expertise. I think the closest vector problem is NP hard under some randomized reduction hypothesis or something. So there are underlying theoretical things for that. But it's mostly efficiency.
Okay, well, with that, I think we will wrap things up for the evening. Let's thank Professor Silverman.
Thank you.
Thank you all for coming.